Morning. In this session of design of compression members, I'll be explaining you the design of shock column subjected to axial load and biaxial moment. In this particular type of problem, the shock column is subjected to an axial load as well as the moment along both the major principal axis and the minor principal. So in this particular type of problem, generally, in the design, we need to assume the longitudinal percentage of longitudinal steel and the section, trial section need to be assumed. So the trial section, the percentage is assumed based on the given data, that is PU, MUX, MUY, and FCK and FY using the charts in SP16. Similarly, the trial section that has been assumed, for the assumed trial section and for the assumed longitudinal percentage of steel, we need to check for minimum eccentricity, and for the assumed trial section and the longitudinal reinforcement, we need to determine MUX1 and MUY1 and check PUZ and alpha N and see that all the data are within the prescribed limit as described in IS 456 as well as SP60. So in this particular problem, we design the reinforcement that is required to be provided for a shock column as shown in the figure. It is subjected to an axial force, an ultimate axial force of 2000 kilonewton and an ultimate moment of 130 kilonewton meter and one along major principal axis and 120 kilonewton meter about minor principal axis. The unsupported length of the column is 3.2 meters. The column size given in this particular problem is 400 millimeters width and 500 millimeter depth. The grade of concrete used is M25. Grade of steel used is Fe415 for the design. The step one in this particular problem is to verification of eccentricity. As you can observe in the problem, they have directly given you the unsupported length of the column and they have not given you any kind of support condition in this particular problem. Hence, we will be considering the unsupported length of the column as L. So, in the verification of eccentricity, for the given unsupported length of 3.2 meters, for the width of 400 mm, for depth of 500 mm, the minimum eccentricity is calculated based on the formula given here, that is L effective by 500 plus B by 30 and 30 mm, the greater of these two. In this, we are getting 19.73 or 20. So we are taking the greater of these two, that is 20 mm. Similarly, in EY, adopting the same formula, we are getting 23.07 or 20 mm. Hence, it is taken as 23.07. Again, from the given axial force, ultimate axial force of 2000 kilonewton and moment along the major principal axis of 130 kilonewton meter and moment along the minor principal axis of 120 kilonewton meter, we have the eccentricity along X and eccentricity along Y, which is 65 mm and 60 mm, which is greater than the minimum eccentricity along X and along Y respectively. So in the first step, we need to verify the eccentricities for the given section, minimum eccentricities, and then for the given load and the moment, we need to find out what is the axial eccentricity. If the axial eccentricity is greater than the minimum eccentricity, we need to consider the calculated eccentricity. Then in step 2, we assume the trial section including the reinforcement. But in this particular problem, the section has already been given. Hence, we will be calculating, we will be trying to understand what will be the approximate reinforcement that is required to be assumed. So here, we already have the width of the column as 400 mm and depth of the column as 500 mm for the reinforcement. Hence, MU is taken by this formula, which becomes 203.436. Pu by FCK and mu by FCK is calculated, and we are using the cover, assuming the cover as 60 mm, and 44 and 45 of SP16, the value of P by FCK is interpolated to 0.06. Therefore, the percentage of steel as per the charts of SP16 is considered as 1.5, which gives me an area of 3000 millimeter square. For this particular area of steel obtained, we are providing 12 numbers of 20 mm dia bars, whose area will be 3769, which is greater than the area required, and the percentage of steel provided now is 1.88%. So P by FCK will be 0.075. Here we have assumed D dash as 60, and hence we have got D dash by D as 0.12. In the step 3, we will be determining the MUX1 and MUY1 for the assumed section and the provided reinforcement. And for the assumed section for provided reinforcement, the PU by FCK BD is 0.4 and P by FCK is 0.07358. Now we get MUX by FCK BD square from chart corresponding to D dash, which is equal to 58 mm, because it is calculated by providing the longitudinal steel. Hence, the D dash by D in this particular problem is 0.116. So we interpolate the values of chart 44 and 45 of SP16 and get MUX1 by FCK BD square as 0.09044, where the MUX1 will be 226.1 kilonewton. So for MUX1, in the similar manner, we get MUY1 as 171.6 kilonewton meter. MUX1 and MUY1 are significantly greater than MUX and MUY respectively. Redesigning of section is not needed because the provided section has got higher moment carrying capacity. And step number 4, we determine PUZ and alpha M. The PUZ and alpha M obtained is 3380.7 kilonewton, and alpha N obtained is for PU by PZ of 2000 by 3380.17 is 0.596. So PU by PZ lies between 0.2 to 0.8, which gives alpha XN as 1.658. And in the next step, we'll be checking the adequacy of this section. We know we have the value, the moment value and the moment required for moment carried by the section both along X as well as along Y direction, and we have alpha N, and here we check this by mu by MUX1 plus mu to the power alpha N plus MUY by MUY1 to the power alpha N, which need to be less than 1 as described in SP16. So in this particular problem, MUX by MUX1 to the power alpha N plus MUY by MUY1 to the power alpha N is equal to 0.9521, which is less than 1. Hence, the design is safe. Alternatively, from chart 64 may be used to obtain MUX by MUX1 and MUY by MUY1 is within the curve of PU by PUZ, that is equal to 0.5916 or not. We need to cross check it. So we know that MU by MUX1 and MU by MUY1, it may be seen that the point is within the curve. This is an alternative method. Either you can use the first method or the second method. But it is always advisable to use the first method, where MUX by MUX1 to the power alpha N plus MUY by MUY1 to the power alpha n should be less than 1. Next, the last step is to calculate the design of transverse reinforcement. As per the clause of 26.5.3.2 of IS 456, the design of lateral ties should be greater than the maximum longitudinal reinforcement provided in the column divided by 4 or 6 mm. Hence, we provide 8 mm dia bars over here with the following arrangements. The spacing of the lateral tie is the least of 400 mm, that is the least lateral dimension of the column, 32 mm, 320 mm, that is 16 times the diameter of longitudinal reinforcement, which is 20 mm in this particular problem, and 300 mm. So the least comes to the 300 mm, hence we provide 8 mm lateral ties at 250 mm center to center.